also how the solution at a particular point is going to influence the solution at a future point in time. Okay, so so that's a couple of definitions. You'll probably on your next homework you'll have a chance to kind of work off of that idea. The next thing I want to talk about is semi-infinite domains. Okay. And if I get to them, maybe I'll talk about what are called energy methods today. Okay. So what have we talked about so far? We've talked about the primary solution method for the one-dimensional wave equation. We've talked about the way that that behaves with respect to the way that characteristics propagate initial conditions, and the way that a point in time, the solution at a point in space-time might be influenced by the value of the solution at points that precede it. Okay. So now let's look at let's circle back to our initial value problem that we were looking at before. Okay. And remember, this is, let's say, for the IVP, UTT equals c squared uxx on x is in R, t is greater than 0. U of x0 is phi, ut of x0 is psi. Okay. Then D'Alembert's solution, okay, tells us that u of xt is equal to a half phi of x plus ct plus phi of x minus ct plus 1 over 2c, the integral from x minus ct up to x plus ct psi of y dy. Okay. And before we look at semi-infinite domains, let me mention just a few properties of this solution. Okay. Note that it has finite propagation speed. Okay. So remember up here, right? If something is happening here, okay, the soonest that this location in X would hear about it, right? Or this location in X would hear about it, right? Is given by some finite amount of time, right? It can't sort of instantaneously propagate that information over here. It's limited by what? By the wave speed c, right? And you say, well, of course you have to have finite propagation speed, but when we go to look at the heat equation, we'll see a situation where propagation speed is infinite, okay? Why? Well, because it's a continuous approximation of, diffusion, so it's not necessarily physical. But the nice thing about the wave speed is you have this reasonable physical property, okay? Another property is that it's a well-posed problem, okay? So it has regularity, okay? Assuming, appropriately smooth phi and psi, okay? We've also talked about the domain of dependence, okay? And this gets at, because it's compact, okay? This is sometimes called the principle of causality, okay? That you can actually look and geometrically see what regions are going to cause changes to other regions, okay? It's not just a whole mess where any particular point in space could affect the solution in another particular point in space, okay? We also talked about the region of influence just now, okay? Also, what we've alluded to is that if psi and phi, okay, have compact support, okay, so does U, okay? And in particular, we saw that here, right? For as long as we go forward in time, right, this region of compact support, well, you still have a region of compact support. It doesn't spread out, right, to be infinite, as you would find in the heat equation, which we will later, okay? So these are key ways that the wave equation is different from the heat equation. We also have a property called conservation of energy, okay, which we'll show later on when we talk about energy methods, okay? So nice properties of the wave equation. We also have, you know, the fact that the wave equation is hyperbolic tells us that we might expect these properties of other hyperbolic equations, okay? So for the next section, and this may be the last depending on how long it takes me, we'll consider what are called quarter plane problems, okay? So everything to this point we've thought of the wave equation living just on the real line, but let's say that we bound it to the quarter plane like we looked at in the transport equation. And given that you've worked homework problems on the transport equation, you might think immediately, well, how's the wave equation going to interact with the boundary? How are those dynamics gonna interact there? How are we gonna deal with that? And first of all, we have to have some information about what's happening on the boundary. So in addition to our initial conditions, right, that live at t equals 0 and x greater than 0, we're also going to have a boundary condition. And let's start with the easiest one we can, just a homogeneous boundary condition, okay? So when you think about this, this is like, you know, a string that's pinned at one end, okay? And then you disturb it, right? But it's nailed down right here, okay? So this is like a string held in place, okay? And this is our IBVP, okay? So what happens, right? Well, first of all, you know, we have a boundary condition. We could have also specified that the gradient of U is 0. And this would be like a case where we have a stress-free boundary. So you basically fix the, in that case, you would fix the string to have 0 spatial derivative at the boundary, but you know, maybe it can slide up and down a wall. So maybe it's held in place into some sort of a slider that sort of slides it up and down. Okay. But we're going to look at the case where the string is just directly held down. Okay. So first of all, the good news, well, for x is greater than ct, okay, we can just use D'Alembert's formula because we're not going to interact with the boundary, okay? So just to get a sense of this, right, here's t, here's x, here's our characteristic x equals ct, right? If we have, you know, some initial condition here, it comes in, it, you know, it does something, it maybe bounces off the wall, okay, as we'll explain later, okay? Anything that's happening on this side of this characteristic is only ever going to be affected by this initial condition. But everything that's up here, right, is gonna have to reckon with this boundary here, right? So that's kind of what we're going to explore, okay? And so, so for x is greater than CT, as I was saying, we just have D'Alembert's formula again, okay? Write it down again, right? A half of phi of x plus CT plus phi of x minus CT plus 1 over 2c integral from x minus CT up to x plus CT psi of y dy, okay? Now, as I was saying, the initial and boundary conditions are going to interact on the region x less than CT, okay? Now, just because D'Alembert's formula doesn't hold doesn't mean we can't just plug in our general solution from before. So if you remember from Wednesday's lecture, what we said is that our general solution is some function f of x minus CT plus g of x plus CT, okay? And so if we plug this in, then we can solve it to find what the resulting solution should be, okay? So we solve to find, okay, u of xt is equal to a half phi of x plus ct minus phi of ct, oops, minus x plus 1 over 2c, ct minus x, x plus ct, psi of y dy, okay? Basically on this bounded region, okay? So how do we get this formula? Okay, I'm giving you the formula that we're going to arrive at, okay? Well, we kind of use the method that we talked about when we derived D'Alembert's formula, okay? So let's look at that again. So remember, we have our guess at the solution, our guess at the form of the solution, okay? We have our initial values, and we have a boundary value, right? We've gotten this solution by knowing that we're trying to solve this PDE. So if we plug it into the PDE, we're just going to get back that, well, yeah, right, this solution works. So you have to now use, in order to specify f and g, you have to plug into your initial and boundary conditions, okay? So let's go ahead and do that, okay? So to show this, basically you just plug into ICs and your BC, okay? So u of x0 is equal to f of x plus g of x is equal to phi of x. U sub t x0 is equal to minus c f prime of x plus c g prime of x is equal to psi of x. And then your boundary condition is now a third condition. And that just tells you that at t, x equals 0, you have f of minus ct plus g of ct is equal to 0, okay? So this is key, right? Because this provides you a link with f of some negative argument and g of some positive argument, okay? So this essentially is what allows you to see how solutions kind of get reflected off of this boundary. So let's see how all this fits together. This is already in a pretty clean form, okay? Let's work on manipulating these two formulas here, okay? So first of all, take the second formula and I'll integrate it up. So I get f of x well, minus f of x, let's say, plus g of x is equal to 1 over c, the integral from 0 to x of phi of y dy, plus some constant a. Okay. Second thing I'll do is I'll note that f of x is equal to g of minus x, sorry, minus g of minus x, according to this formula, right? What did I do? I just replaced x with minus ct. I could use a different variable, but x is fine, okay? And now we have a relationship between f of x and g of minus x, okay? So we just have to figure out how to take this equation, and this equation, and put it all together to get formulas for f and g in this case, okay? So the first thing we'll go ahead and do is we'll combine the second equation with the first equation, right? So take the first equation, let's say minus the second equation, and we end up with 2 f of x is equal to phi of x minus 1 over c integral from 0 to x psi of y dy minus a, okay? So f of x is equal to a half phi of x minus 1 over 2c integral from 0 to x psi of y dy minus a over 2. Okay, so something that's starting to look like the solution is starting to emerge, okay? And then if I take the first plus the second equation, okay, then I get 2 g of x is equal to phi of x plus 1 over c integral from 0 to x psi of y dy plus a. And then, of course, we can divide by 2, right? Okay, so we're getting there, right? But we still haven't used our third condition, okay? And that's going to be, and what do I mean by this? Well, if I try and take what f of x minus ct is, okay, remember that that's going to be equal to phi of x minus ct over 2. And if x is less than ct, this is going to be a negative argument, and I don't have any information about that particular value, right? Same thing here, right, with this integral, right? I don't have any information about psi for when the argument of it is less than 0, right? Because it's only defined on x greater than 0, when its argument is greater than 0, okay? So what I need to do, right, is figure out what f of x minus ct is, right, when x minus ct is negative, right? So f of x minus ct, another way of realizing that is just to say, well, it's equal to minus g of ct minus x, right? And that's just me applying the third formula that I have there, okay? So in that case, right, if I want f of x minus ct, okay, then the only thing I have to do is compute g minus g of ct minus x, okay? So let's put all this together now, okay? So I have that f of x minus ct is equal to a minus g of ct minus x, which I know is going to then be equal to the negative of this evaluated at ct minus x. So it's going to be a half phi of ct minus x plus 1 over 2c of the integral from 0 up to ct minus x, plus a over 2, okay? And it'll be the negative of all of that, right? Okay. So that's my f of x minus ct, and then g of x plus ct is just going to be a half phi of x plus ct plus 1 over 2c integral from 0 up to x plus ct psi of y dy plus a over 2, okay? So now when for x is less than ct, I compute this, right? I have f of x minus ct plus g of x plus ct. What do I get? Okay, I just add these two things together, right? So first of all, I see that those two terms are going to cancel, okay? And I get a half of phi of x plus ct minus phi of ct minus x, okay? And plus 1 over 2c, the integral from ct minus x up to x plus ct of psi of y dy. And if I check back at my formula that I wrote down before, indeed, that's exactly what I get, okay? So I have now the solution at x less than ct. I have the solution at x greater than ct. I put those together, and that's my piecewise solution, okay? And note, right, that it works with the boundary condition because u evaluated at 0t is a half phi of ct minus phi of ct plus 1 over 2c integral from ct up to ct psi of y dy, and that's equal to 0, okay? So everything works. This is often what's called the odd extension, okay, of phi and psi, okay, to the real line, okay? And essentially, our waves are going to cancel at x equals 0. Okay, so what happens is, you know, you have a wave that's propagating along, right? It hits the boundary here, and then it actually flips as it then propagates away again, okay? So that's why it's the notion is of odd extension, is because essentially, you know, this displacement upwards gets displaced downwards when it interacts with the boundary. So this is what's happening as a characteristic hits here and bounces off, okay? We can also deal with cases of non-zero boundaries. I'll just wrap up with that. So in the case of a non-zero boundary, okay, utt equals c squared uxx. Again, let's say we're in the quarter plane, and we have initial conditions in position and velocity. And let's say that we have that u of 0t is equal to h of t for t greater than 0, okay? In this case, you have an additional term that propagates boundary data into your upper quadrant there, okay? Let's look at just what happens just if phi and psi are 0, okay, well then you can think of, h of t as inducing string motion, okay? So the idea is that maybe the string starts off stationary, but then as this sort of moves up and down, right, it's going to cause the string to be displaced up and down it, right? So it's like you're holding the end of a string and you're moving it up and down. That's going to cause the string to have waves that propagate towards its end. Okay. So the idea then is that you have u of xt. It's just going to be given by these rightward propagating waves that you get. And in this case, f of minus ct is going to equal h of t, right? This is our boundary condition. And so if we convert just to f of xi is equal to h of minus xi over c, okay? And then this means that u of xt is going to be equal to h of ct minus x over c, okay? So whatever's happening at the boundary, that's just propagating out and to the right. So here's a case where you just get sort of rightward propagation of information, okay? And in general, let's just close with this. In general, right, if we just take this initial value problem or initial boundary value problem, okay, and let's call it, I don't know, double dagger or something like that. This is going to have solution given by just the superposition, okay, or sum of the solution when h is equal to 0 plus h of ct minus x over c, okay? And you can on your own check the initial and boundary conditions in this case, okay? So that's it for this lecture. So what have we talked about so far today? Well, we talked about how to use D'Alembert's formula to prove continuous dependence, okay? We talked about how to think about how initial conditions propagate according to regions of influence and domains of dependence, and how we expect support to remain compact because of the way that initial conditions propagate in the wave equation, similar to how they do in the transport equation. We talked about this technique of basically finding solutions to initial boundary value problems for the wave equation. And the general idea is just to take your general solution and plug it into your initial and boundary conditions and manipulate those equations in order to back out the formula for f, in particular, in the region of interest, basically between the boundary and that characteristic that divides your domain, this region right here, right? And lastly, we talked about the effects of inhomogeneous boundary conditions on solutions. And luckily, you just have solutions that are just a superposition of the effect of the boundary data, and then just your homogeneous solution. Things get a bit more complicated if you have a flux rather than just a set boundary condition, a position-based boundary condition. But you can still use these sort of techniques that we built up today in order to address that problem.